Welcome to our 5th session on transition metals. This is going to be quite a short session, but it's a really important idea, and it's something that's frequently mixed up when students attempt to do questions associated with transition metals. And I'm going to do it by working through 3 examples. So we need to be able to work out the complex that's present in an aqueous copper 2 chloride solution. So let's think about the ways we can write this. First thing we need to do is basically remind ourselves what the formula of copper 2 chloride is, and it's CuCl2, and then I'll put AQ after it to show that it's an aqueous solution. How have I come up with CuCl2? Well, remember that the Roman numerals 2 tell us that copper is in a 2+ oxidation state. We know that chloride ions have a single negative charge, so I need 2 chloride ions for each copper ion in this case. When it's dissolved in water, the copper ions and the chloride ions separate from each other. So we dissociate in water, and we have aqueous 2+ copper ions, and 2 for every copper 2+, we have 2 aqueous chloride ions. Now, we've learned in previous sessions actually that copper 2+ aqueous actually exists as a complex, and it exists as this complex. This is actually the hexa-aqua copper 2+ complex. Now remember, we put square brackets here to show that everything inside here is a complex. We've got the copper ion, we've got in brackets water, and water is acting as a ligand here, so that's where the oxygen atoms in the water molecules form coordinate or dative covalent bonds to the copper ions, and there are 6 of them. And the 2+ here shows us the overall charge on the complex. The overall charge on this complex is due to the 2+ of the copper ion, and the water ligands are neutral, so that 2+ in this case is due just to the charge on the copper. I could draw this out like this. So we've got an octahedral geometry because we've got 6 water ligands. So I haven't drawn this in 3 dimensions, but as I said previously, it's not too much of an issue as long as I put a bond angle. So the bond angle between any oxygen copper oxygen is going to be 90 degrees, and I state that this is octahedral. Remember, the reason it's octahedral, because that oct means 8, is because if I were to put faces onto this shape, I'd have an 8-shaped, 8-sided face shape. So the most important thing here is for us to recognise this. This is the complex that we're interested in. The chloride ions are not forming dative covalent bonds to the copper ion. They will simply be spectator ions for the most part, and they will be in the solution. So we're not particularly interested in these. They don't form a complex, they don't form dative covalent bonds, and that's very important. Let's have a look at our next example. So this is going to be largely the same, it's just worded differently. So previously we had an aqueous copper 2 chloride. This time we're told we've got a solution of CoBr2. So let's pick this one apart again. Remember that the Br- ions, there's 2 Br- ions, these do not form dative or covalent bonds to the cobalt 2+ ion. We can think of them for most part, they are spectator ions, they will be hydrated, there is no dative covalent or coordinate bonding taking place. So actually what we're left with is the CO2+ ion. How do I know that it's a CO2+ ion? Well, we've worked out that bromide ions have a single negative charge. There are 2 of them, so therefore to balance that up for this neutral formula here, we should have CO2+. So in fact, the complex present in this solution is actually a hexa-aqua cobalt 2. We could draw the structure again, but it would be exactly the same as the previous one. It would be 90 degrees, it would be octahedral, and instead of copper we just have cobalt. So all aqueous complexes are octahedral and they have a 90-degree bond angle. Let's have a look at our last example. This is actually the formula for hydrated copper sulfate. So this is another way we need to be able to work out the complex that's present. So what we've got here is the complex, which has already been written out for us, and a sulfate ion. Now hopefully we know that a sulfate ion has a 2- charge, therefore the formula on the complex must be 2+ due to the copper ion. So the sulfate ion again, I should have written this as aqueous actually. The sulfate ion again is going to be a spectator ion. It's not involved in the complex, and that it does not form dative covalent bonds or coordinate bonds. Remember that those words are interchangeable for us. So it does not form dative covalent bonds. So the formula of the complex present is simply this one here, and again if we were to draw the structure it would be an octahedral geometry. So just to summarize, the purpose of this is for us to recognize the aqueous ion that is present when we look at a transition metal salt. So copper 2 chloride, aqueous copper 2 chloride. What we're interested in transition metal chemistry is the hydrated complex. Remember, the chloride ions are not involved in dative covalent bonding. The same here, the bromide ions in this formula are not involved in dative covalent bonding. They are not involved in the complex, so we have that. And similarly here, the sulfate ion does not form a dative covalent bond. So just to try and get some understanding on here are 4 questions. If you would like to pause the video and do them now. And now I'll very quickly, hopefully you've done these, I will have a go at answering them for you. So copper 2 iodide is CuI2. It's a solution, so it's aqueous. The complex we're interested in is hexa-aqua copper 2. Square brackets there, so aren't quite as square as they should be. Complex present in this solution. Remember, these do not form dative covalent bonds, so the complex present is the hexa-aqua cobalt 2. How do I know it's 2+? There's 2 chloride ligands. Sorry, that's a mistake. 2 chloride ions. Each of those have a negative charge, which means this must have a 2+ charge. The water ligands are neutral, so that 2+ is due to the cobalt. The chloride ions present in this complex, the Cl- ions do not form dative covalent bonds. The dative covalent bonds are actually present in this part of the formula, so the complex where the oxygens are forming 6 dative covalent bonds to the copper 2. And the formula of the complex present in FeCl3 is Fe H2O6, and so that's the hexa-aqua ion 3. So how do I know it's 3+? We've got 3 times chloride ligands, so the ion must have a 3+ charge. The water ligands are neutral, so that 3+ charge is due simply to the ion. Thank you very much.